This will be a very small video on the introduction of semiconductor. Semiconductor means the conduction level is less than that of a conductor. We know that electrons are the means of current carrying. The flow of electron is the current flow. So a good well-known conductor is copper, and it has 29 electrons. In one copper atom there are 29 electrons. So if we look at a copper atom, the first orbit has 2 electrons. So if we go by the formula 2n square, first orbit has 2, second orbit has 8, and the third one has 18, because 3 square 9 times 2 18, and the last one just 1. So this last orbit has only 1 electron, and the attraction between the nucleus and this electron is very less. This electron is virtually free, and this is very much ready for flow, for free flow. So whenever there is an electric field, I mean this is just flows around in a copper solid, copper metal. There are many atoms, of course, and there are many electrons as well, but they move around randomly. But when there is an electric field, aligned force, electric force in terms of an electric field, a voltage, there is a flow of current. So that's why copper is a very good conductor, and similarly there are other conductors. Now semiconductor has a different, a very common semiconductor is silicon, and silicon has, this is a silicon atom. Its first orbit 2 4 2, and the second one has 8, and the third one has 4. So basically this one has, a silicon atom has 14 electrons, and this is how in an atom the electrons are arranged. As we can see, the last orbit has 4 electrons, so it would like to complete the octet. So what happens in silicon, 4 silicon atoms like this form covalent bonds. So this one is sharing electron with these two, are sharing electron, these two share electron, sharing and sharing. These are the shared electrons, and that's how this silicon atom has completed octet, the last shell. Now this one is still a bond, but at room temperature there is virtually no free electron. But if the energy can be increased at higher temperature or with some other energy, what happens is some of the electrons may be available for conduction, but it is not as good as the conductor, of course. So conduction level is very less. However, we will see later that this conduction can be further increased by adding something called, we can call impurity. So adding another material inside a semiconductor, inside silicon material, so that is called doping the material, and that increases the conduction much more. And it's still a semiconductor, of course, but the conduction can be controlled. That's where the conduction electrons, number of electrons, can be controlled that way. So basically what happens, instead of looking at these atoms as such, when we have a solid copper or whatever, the solid material, full material, we have plenty of atoms. So what happens is, we know according to Pauli's exclusion principle, so whenever we have 2 copper electrons, theoretically this electron energy and the another one will have the same energy, but that is not possible according to Pauli's exclusion principle. No 2 electrons can have all the same quantum numbers. So what happens is actually, instead of the whole energy, instead of having those discrete levels, they smear out to an energy band. So we get the energy bands. It's like that. So this one is pretty much, I will draw first this one. So this one and this one, we have valence energy and we have conduction energy band. So valence band is, all these ones are valence electrons which are bound to the nucleus, which are under the attraction of nucleus and are not free for conduction, and this one is conduction electron, so it's in the conduction band. So for a metal, what happens is, there is an overlap of conduction band and valence band. So basically if this one, we can say the conduction band here, the valence band here. So basically we can see there is an overlap. So all of the bottom ones are, these ones are valence band and this one will be conduction band, but there is an overlap. As a result, what it means is that there are already electrons available for conduction, while this one is that of a semiconductor. So this one is the valence band and this is conduction band. When we say valence band, conduction band means all the electrons below this energy are that of valence band. So they are all forming a band instead of discrete levels, and that is happening because of the so many atoms together. So energy, they just spread out to a band of energy. Similarly, the conduction band is any electron above this energy level is available for conduction, so that's conduction band. So energy, of course, is increasing this way. When an electron from here, from the valence band, gets sufficient energy, the energy increases and it goes to the conduction band, and once it is in the conduction band, it is free for conduction. While in metal we can see electrons are already available for conduction, so just we apply an electric field and it goes into conduction. And this one I will redraw the insulator one. Let's forget this picture here. So I will redraw. What we can see that this one is that of a semiconductor. So what will happen for an insulator? The band gap is much larger. So this one is called the band gap, forbidden gap or band gap. So no electron can be here. So from this energy level it has to go to that energy level, this one to that one directly. So this is a forbidden gap, and this forbidden gap for a semiconductor is not much. It is definitely, there is a forbidden gap. In metal there is no, in a conductor there is no gap as such, but in semiconductor there is a small gap. For silicon there is a gap, for germanium is another one, there is a gap, it's like 1.1 electron volt, whatever, I will talk about that later. But for insulator this gap is very high, so high that basically valence electrons, there is no normal way that the valence electron can go into the conduction band to have a conduction, enough electrons for conduction. So that's why insulator means that the ones that are not suitable for conduction. So yeah, this one is the pretty much the very basic. Video has already become very long, so I just wanted to touch the very basic in this first video.